Hi, this is Marc Hamilton with NVIDIA.
And I'm Gilad Shainer, also with NVIDIA, and actually came to NVIDIA through the acquisition of Mellanox.
Well, Gilad, this is the first ISC where we have Mellanox and NVIDIA together, and a great time to be celebrating 25 years of scientific computing acceleration. But so much has changed in those 25 years, and it's great to be here today at the Exhibitor Forum digitally and talking to all of our customers and partners about what we're doing in this space. So much has changed in 25 years in scientific computing. You used to just run your simulation on a supercomputer and that was it. Maybe do a little bit of visualization at the end. And of course, simulation is still important at the core of scientific computing, but so much has changed. If you look at just all of the supercomputers that are being reprioritized for COVID-19 work today, half of the work being done is simulation, and the other half is applying AI to the front end of those simulations to steer the simulation, to decide what parts of the problem space should you simulate. So we're super excited about all the work being done on the NVIDIA platform in AI and combining that with simulation. And then, of course, there's the, I think the really large scientific instruments, the Large Hadron Collider, Square Kilometer Array. Researchers haven't thought about those so much at the edge. They've thought about that as, well, this is the core of what they're doing. But think about in any research center across the world, you have all sorts of edge instruments, anything from a tabletop or even handheld genome sequencer, electronic microscopes, all sorts of sensors of all types that are involved in an experiment. And when a researcher runs their experiment, they capture all of that. And half the time, by the time they leave the center, they've had to throw away most of their data. They pick out certain parts that they think is important, and they take it home to their home institution. It's not recorded anywhere. It's not saved for posterity. And the challenges is that it's just too hard to take all that data from the edge back into the core data center in the simulation. And so applying AI at the edge is becoming even more important every day.
And of course, the network is the heart of everything here. Right? So during computation at the edge, you need to move the important data from the edge to the data center. You need to move data from the data center to the storage, from the storage back to the data center, to the analytic devices and things of that sort. So that the network is the key element that enables the data movement. And if you bring or deploy very big pipes of data that can run in 100 and 200 gigabit per second, extremely low latency, and also network that has compute engines, so it can actually participate in the data analysis, then you can form a great solution that covers everything from the edge to the analytics, storage, and the data center.
So what do you think about what NVIDIA is able to do now with Mellanox technology is really optimize across the full stack. Starts with the networking. That's what brings all the data together. You, of course, have the compute, and then you have the acceleration. But we don't start designing a solution to scientific computing at this lowest level of the stack. We really think from the beginning about extreme scale, about data center scale, about supercomputer center scale. And those decisions, when you think about the entire supercomputer, end up trickling down, right? Your network bandwidth that you need to connect the different server nodes, that has an impact on the processor design. It has an impact on the packaging inside the server. It has impacts on the cooling of the node, the cooling of the data center. And then finally, everything that we're doing today is increasingly software defined. Networking, of course, has software defined components. In storage Software-defined storage is everywhere. It's not enough anymore just to have a large parallel file system. And finally, putting these all together, right, to continue delivering those X factor speedups year after year for the hardest scientific computing problems. It's not enough anymore just to have a GPU and a CPU. Today, in our server nodes, in our supercomputers, we're adding DPUs, or data processing units. Gilad, tell us a little bit about what Mellanox is doing on the DPU front.
Yes, the DPU is a key component in the transition of the data center from being a very CPU-centric to be more of a data-centric. So if you want to be able to analyze the growing amount of data, to do it effectively, to find insights in real time, and to overcome performance bottlenecks, you cannot continue and move data to the compute. You actually need to do the opposite. You need to move compute to the data. And the DPU, or the data processing unit, that those elements refer to compute engines that now being implemented or added to the network devices and enable the network devices to participate in the job runtime, to be able to do data analysis on the data as it's being transferred within the network. And the Mellanox network, or for example, the InfiniBand devices, includes two kinds of data processing units. One kind are data processing units that are very dedicated to specific algorithms. For example, data processing unit for data reductions or data aggregations, which is a key thing in high performance computing and in deep learning. There are other compute engines that are more generic, such as ARM cores, that enables users or application owners to actually run their own algorithms or to program the network to fit their own algorithms or to optimize their applications. So that's the adding of DPU, and the combination of DPU, GPU, and CPU together forms the new generations of data centers, the data-centric data centers.
So when you put that all together, what do you end up with? At ISC this year, we're very happy to introduce to the world Selene. Selene is our new DGX A100 SuperPod. It was built in only 3 weeks, and it ended up being a top 10 supercomputer. Quite an amazing achievement in and of itself. This is a picture of our actual data center in Santa Clara, where Selene lives. It's built out of 140 DGX A100 systems. Each DGX A100 has 8 Ampere architecture GPUs, so 1,120 A100 GPUs, and 170 Mellanox switches, a total of 4 petabytes of high performance storage and 700 petaflops of AI flops of power to train previously untrainable models. It's really interesting that 140 DGXs and 170 Mellanox switches. Just doing the math there, we've got 10 HDR connections for DGX. 170 seems like a lot of switches, Gilad. How come we have that many switches in the SuperPod?
Well, we're just before that, you said 3 weeks to build the top 10 supercomputer. That's amazing. 2 weeks to have a top 10. That's amazing. And then yes, every DGX has 10 adapters or 10 InfiniBand adapters that can bring 200 gigabit per second each. So that's a lot of bandwidth. And you're right. The 170 switches are a little bit more than what you actually need to connect 140 DGX boxes. But the reason for that is that we wanted to have room for expansion. So it will be easier to add more DGX boxes, easier to scale the system, and we can grow the systems to hundreds and thousands and tens of thousands of DGX boxes and actually enable the impossible, as you mentioned.
You know, this is, I think, a great example of the lessons learned of working at supercomputer center scale from NVIDIA and Mellanox working together. This is our third generation SuperPod, the third generation to be on the top 500 list, and we've improved each time in our placement and positioning. Now, of course, it scales down as well as up. So there's a basic scalable unit in the SuperPod that is 20 DGX A100s. And one of the lessons learned in earlier SuperPods is as we grew, we didn't want to go through it. We wanted to be able to grow incrementally without having to tear apart that network fabric, right? And so starting with that 20 unit scalable unit, you can grow 20 units at a time, all the way up to 140 DGX A100s. And there from then, in increments again of 140 at a time. As you said, thousands of DGX A100 systems. So it's a great design, it's future-proof, and scales not only up, but scales down as well. So we're so excited about this system and having a blueprint that customers can just pick up and move into their own data center in 3 weeks or less.
Yeah, so 3 weeks to a top 10. That's something that people should remember. And of course, the ability to scale up as you need or scale down as you need. That's a great design for any supercomputing center around the world.
Now at the core, of course, we have to talk about the NVIDIA A100 Tensor Core GPU. Really, besides the specs here, 5 miracles to the GPU that make it possible. The first is, of course, using 7 nanometer technology, we were able to pack 54 billion transistors into the A100. That's more transistors than we've ever put in any GPU previously. Second, this is our third GPU, third generation Tensor Core that we've added. A few features compared to Volta that we've managed to pack into the Ampere Tensor Core. First of all, we've brought in int8 inference performance by adding the int8 Tensor Core features that we introduced in the Turing architecture. First time for a large data center GPU. But finally, for all of our HPC customers, we didn't forget you, right? There's a lot of people, Jack Dungera, none the least, that use the 32-bit Tensor Cores to work on iterative refinement solvers, working on HPC AI, but it wasn't true 64-bit, right? You use regular 64-bit math when you needed it, and then had to drop down or could drop down and use 32-bit Tensor Cores when available. With Ampere, we have full IEEE FP64 compliant Tensor Cores that will accelerate HPC apps out of the box. Third, and this is equally important for AI applications, as well as many scientific computing applications, we spend a lot of time focusing on accelerating sparsity, sparse matrix multiplication. So between the sparsity features inside the GPU at the hardware level and cuSparse and our other CUDA-X libraries, we're able to deliver amazing increases in sparsity performance. Fourth is when you go into a large data center, a capability system, you're going to try to use the entire data center, the entire supercomputer to run as many jobs as you can. But many supercomputer centers are more capacity-based. They're running a lot of small jobs. And with 54 billion transistors, for some users, they actually don't need a full A100. So with the new feature we call multi-instance GPU, or MIG for short, we're able to take the A100 and divide it up into 7 independent, physically isolated GPUs. So on a DGX A100, it can be up to 56 independent server partitions. And finally, because on the DGX and our HGX OEM platforms, you not want to only subdivide the GPU, but you want to put multiple GPUs together. So we enabled the A100 with our 3rd generation NVLink and 3rd generation NVSwitch to provide the highest performance GPU to GPU interconnect, really designed as a memory interconnect to let all the GPUs connected with NVLink inside a server work together as a single large GPU.
And let's not forget the PCI Express Gen 4, which is a great match for the 200 gigabit per second HDR InfiniBand, which then enables to connect multiple boxes together and build the best supercomputer that people can build today.
You know, speaking of PCIe Gen 4, that's certainly an area where Mellanox had that out a little bit before us. And again, really looking forward to combining our efforts moving forward in some of those areas like supporting interconnect standards like PCIe. When you put that all together, right, it's easy on PowerPoint to say 54 billion transistors, peak performance can be this much faster. But again, peak performance doesn't mean anything, right, to scientific computing. What that scientist cares about is how long does it take to get my job run? How fast actually can I use that processor, that node, that supercomputer? So again, compared to V100, here's our speed up on high performance computing apps. We've taken that 2.5x raw performance in FP64, and we're able to deliver over 2x in actual real life performance. And again, LinPack top 500, that's not necessarily the best measure, though when you see the final rankings of Selene, I think we did fairly well there. We did great there. But on real apps, this is what I'm most proud of. This is what scientists each day are going to value. And so some of our first A100 systems that shipped in the DGX A100, they actually went out to Argonne National Labs and were put to use the day they were delivered, going through and working on COVID-19 research. A great use of all of those transistors and all of the billions of dollars of R&D that went into the Ampere technology. And of course, on AI training, which is important for so many of our customers, not the least to be our HPC customers, 6x speed up out of the box. A couple of key technologies that allow this, and is our new data format we call TF32. TF32 automatically knows and can figure out when to use lower precision without requiring any changes in the code. So here's some examples on our comparison versus Volta in automatic mixed precision on Volta to Ampere and to out-of-the-box FP32 to TF32. And again, without requiring any changes to your code. So just delivering amazing performance for scientific computing.
And of course, the next part in the system is, of course, the network. And InfiniBand, or the 200 gigabit per second HDR InfiniBand, connects all of the GPUs together to actually form the large supercomputer and ensure that everything's work in a very effective way. InfiniBand delivers today 200 gigabit per second end-to-end, very extreme low latency, probably the lowest latency in the market today, with very high message rate. And of course, RDMA or GPU direct RDMA that enables to move data directly from GPU memory to GPU memory or from CPU memory to CPU memory. InfiniBand also includes advanced adaptive routing and congestion control that enables a very efficient data movement and brings the network efficiency almost to 100%. The in-network computing engines, the engines that enable the network to process data as it moves, brings capability or brings performance advantages to MPI, bring performance advantage to nickel, for example, and helps to accelerate application performance. One of the key technology of in-network computing is Sharp. And Sharp is the name of the technology that actually enables the switches to build aggregation trees or virtual aggregation trees on the network and to do the data aggregation and the broadcast of the results back to the endpoints. Shield is another key element of InfiniBand, which bring self-healing capabilities and enable the network not just detect issues or failures, but actually to overcome those failures at the network level and do it very, very quickly. So the jobs doesn't really notice that something happened and the jobs will continue to run. And let's not forget that InfiniBand is a standard technology. It's provide backward compatibility, forward compatibility, open API, start APIs, which protect data center investment and enables data center owners or IT managers to connect previous generation to future generation and run the same software, the same drivers, the same applications across multiple generations of the network.
So this is the second top 500 list. So we've had 200 gig HDR InfiniBand on the list, and we're expecting a lot more 200 gig clusters this time around. Sharp is really one of the great examples of where NVIDIA and Mellanox have been working together. Sharp, of course, runs those reductions in the network switch. If you think about it, a lot of software is trying to do that inside the node. In fact, the NVIDIA software that works on that is Nickel, the NVIDIA Common Collectors Library. And that understands the topology inside the node as well as outside the node. So as you can expect, Nickel needs to be aware of Sharp and work with Sharp and be optimized in conjunction with Sharp, tuned with Sharp to provide that highest level performance. And so we've been hard at work the last 6 months working with Mellanox on tuning Sharp for these sorts of MPI and AI data center types of applications, and some great results. Gilad, you want to talk about these?
Yeah, of course. So Sharp enables performance increase for both the scientific or the traditional HPC applications running over MPI, and of course also AI applications running over Nickel. On the left side, we're seeing a performance results from the Niagara supercomputing, which was built in the University of Toronto, and it's probably still the fastest supercomputer in Canada. We have run MPI all reduce operation on the entire 1500 nodes using all of the cores in every node. So we had 60,000 MPI ranks running a reduction operation, and Sharp, or running MPI all reduce on the network, increased the performance of that operation by 7x. That's an amazing number. And it's not just reducing the time dramatically, it's also reduced the data motion. And now you have less data that needs to move. So everything becomes much more efficient. And Sharp is one of the key elements that brings a lot of performance advantages to MPI or applications running on top of MPI. Nickel, on the other side, also utilize data reductions. And working together, we have brought the capabilities of running Nickel on the network, or ability of Nickel to use Sharp for doing reductions in the network. And one of the performance examples is GNMT, which is part of the MLPerf benchmark. And we can see that on 24 DGX boxes, Sharp enables almost 20% performance increase. So think about it, you paid a lot of money of building a data center, and now you get 20% more on the millions of dollars that you invested in a data center. That's amazing.
Well, you know, Gilad, we can't announce all the fun new benchmarks today here at the show. We're still working on MLPerf, and it'll be a few weeks still before the next round of MLPerf numbers are public. But we're really looking forward to those. These performance numbers that you show here, of course, as the footprint says, these were on DGX1, or Volta version of DGX1. And so, of course, what we're testing today on Selene, or DGX A100, and I'm super excited about the preliminary results We'll share the final results when MLPerf publishes them.
And we're all looking forward for that.
So DGX A100, we started talking about the supercomputer, the DGX SuperPod, and let's jump down and talk a little bit, give you a little bit more detail about the DGX A100. Of course, starts with 8 of the NVIDIA A100 GPUs. This gives us a total of 320 gigabytes of GPU memory distributed between the 8 GPUs. Now, those are via NVLink with 6 NVIDIA NV switches. That provides full all-to-all bandwidth for the GPU memory between all of the GPUs. And finally, DGX A100 comes standard with 9 ConnectX-6 HDR connections. 8 of those are used for a compute fabric to build your compute cluster for larger nodes. The 9th is used for management and storage networks is a separate network. And there's 1 spare slot to add a 10th ConnectX-6, is what we're actually using in the SuperPod. It, of course, has 2 of the most powerful CPUs. For DGX A100, we picked AMD's new 64-core CPUs, and we added a terabyte of system memory. And finally, topping it all off, we added 15 Gen 4 NVMe SSDs.
So we talked about the A100, and we looked on the performance of it, and we talked about the network, and then we put those together, and we got the DGX box, and then we can connect the multiple DGX boxes together and build the large data center. So one piece is missing, and that piece is the management piece. And we are very happy to announce the new generation of Mellanox or NVIDIA Mellanox UFM, which is the Unified Fabric Manager platform that now combines telemetry information that it can capture from the network with AI to bring capabilities that were not be able to be done before. And by combining the telemetry information and the AI, the UFM Cyber AI can now learn the heartbeat of the supercomputer. It can learn how the supercomputer operates. It can find performance degradations over time and create alerts. It can predict failures before those failures going to happen. And that gives the capabilities of predictive maintenance to the IT managers so they can come and actually fix things before they happen. So the data center will not go down and people will be able to save a lot of money. But not just that, not just doing predictive analytics and to prevent failures. UFM Cyber AI can also detect abnormal behavior because it knows the heartbeat of the system, and any change in that heartbeat means that something happened. And by detecting abnormal behavior, we can bring security to supercomputing and be able to detect any malicious usage before it makes any impact. The system can also bring other security elements such as cable management or security for cable management. So if someone change the location of the cable, it can detect it and give the alerts. So Cyber AI brings the next level of management, of network management, ability to predict failures, and ability to protect supercomputing. And that's going to dramatically optimize OpEx for supercomputing. Now, here's a few examples of what UFM Cyber AI can do. So it starts from looking on the network setup and validate that everything connects to where it should connect. It also secures the cable management or brings secure cable management. So if someone moves the cable, it will detect it and actually provide alerts to the IT managers. It can do provisioning of the network. It does traffic monitoring. It can find congestions, and it can help solve those congestions. He checks the health of the data centers. It is doing monitorings for faults and giving alerts. It detects any performance degradations and any profile changes, and gives alert for abnormal system behaviors or potential system failures to the IP managers. Then the IP managers can go and actually manage the data center or fix elements before something may happen, and much, much, much more. I do encourage you to look for the more information about the UFM Cyber AI and see all the benefits that that platform can bring to your data center.
So it's been amazing 25 years. I can't imagine what the next 25 months will bring, much less the next 25 years. But again, one thing for sure, we'll continue to optimize across the full stack. We'll work towards extreme scale and deliver X-factor speedups in a software-defined and secure world.
Yeah, and we started this session looking on the data center or the superpods. And then we went and actually looked on each of the components. So we look on the A100, we looked on the network, on the DGX boxes, and the UFM Cyber AI for doing management. And now we're back to look at the data center as a whole. You get a great performance speedup that brings the capabilities of enabling the next generation applications, much further scalability, an ability to do analysis of things that could not be done before. You have the full stack, everything from the compute, the networking, the drivers, the frameworks, the applications, everything that you need in order to run your applications on top of that. You can start with a small scale, you can go to the large scale, grow as you need. Bring more computing engines, add them to the network, and actually fit what the users need or the application needs. And of course, UFM Cyber AI, predictive ability to foresee the future, fix the data center before something happened, and not less important, now bringing security to supercomputing. I think it's a great combination of technology, Marc, and we are very, very excited to work together.
Thanks, Gilad.
And with that, we want to thank you for listening. Thank you very much.